Okay, welcome to lecture 18, last lecture of chapter 4. We're going to be talking about reaction yields. Now, when you have a balanced reaction, that shows you the ideal ratios of the reactants and products and everything to one another. That's not necessarily the ratio you're actually going to have. So, for example, going back to that good old standby, water, 2H2 plus O2 yields 2H2O. If you have exactly 2 moles of H2 and 1 mole of O2, you're going to get 2 moles of H2O. What happens if you have 3 moles of H2 and 2 moles of O2? Well, that's a slightly different matter. Okay? What you're going to get is 3 moles of H2O, and you're going to have half a mole of O2 left over. That's because you don't have the perfect 2-to-1 ratio. You have more oxygen than you need for the amount of hydrogen you have. Okay. You could say that the 3 only needs 1.5 moles to react, or the 2 moles would need 4 moles of hydrogen to react with. So either way, what this means is that hydrogen is, in this scenario, your limiting reagent. Okay. Reagent is just another word for reactant. Okay. So what it's saying is that this is what's putting a limit on what you could produce. The other one, oxygen, is present in excess. Okay. There's more than you need given the amount of hydrogen you have. Another way I'd like to write this is LR for limiting reagent and XS for NXS. Now, let's go ahead and what if you had 10 moles? Actually, let's go ahead and make it molecules. 10 molecules of hydrogen and 8 molecules of O2. How much water could you produce? Well, what the reaction is saying is that you're going to consume 2 of these, 2 hydrogens, for every 1 oxygen you produce. Every cycle, every time, you run through there. So, first time this happens, you get 8 and 7 plus 2 H2O. Then 6 and 6 makes 4 H2O. 4 and 5 makes 6 H2O. 2 and 4 makes 8 H2O. Finally, 0 and 3 makes 10 H2O. So with 10 molecules of hydrogen and 8 molecules of oxygen, you can produce 10 molecules of water, and you'll have 3 molecules of oxygen left over. It's the exact same math if it were moles. But there is an easier way to do this, or at least a more direct way. Let's look at a different reaction. So we have N2 plus H2, another of my favorite standbys, goes to form NH3. Okay. So for this one, let's go ahead and say we have 20 grams of nitrogen and 40 grams of hydrogen. Which one is the limiting reagent? Okay. Which one is the limiting reagent? Which one is present in excess? And how many grams of NH3 will you produce? Okay, first things first, convert to moles. Always convert to moles first thing. So we have to divide by the molar mass. So divide by 28.02 grams per mole. Divide this one over here by 2.016 grams per mole gives us 0.7138 moles and 19.84 moles. I'm guessing I made this one a little bit too obvious, a little bit too on the nose, but I'm going to go ahead and I'm just going to keep on going. So now that we've converted to moles, we divide by coefficient. Okay. So that means we divide this guy by 1, divide this one by 3, so 0.7138 versus 6.614. All right, so this one is really, really painfully obvious, okay? You have a limiting reagent over here versus the excess reagent over here, okay? So that means that the moles of nitrogen is going to limit the reaction, and you're just going to have a heck of a lot of hydrogen left over. So now we have done this, we ignore these. Okay, that's just for figuring out limiting reagent and in excess. Okay, so this is the number you work with for all your stoichiometric calculations. Okay, in order to determine everything else that comes after that, you're going to work with the original number, not the number that's been divided. Okay, and I'm going to go ahead and add another bit of problem. How many grams H2 left over? It's only slightly more complicated. Okay, so first we need moles of NH3 produced. This is a straightforward stoichiometric calculation. Okay? 0.7138 moles of N2 times, going 2 goes on top. It's 2 moles of ammonia for every 1 mole of nitrogen. It gives us 1.427 moles of ammonia. But I asked for grams, so we'll do the molar mass calculation. That is times 17.03 grams per mole. Gives us 24.03 grams of ammonia produced by this reaction. So that is based on the limiting reagent. Now, how much hydrogen will be left over? So first, how much is used? Moles H2 consumed. That is what you figure out using the limiting reagent. So 0.7138 moles of nitrogen times 3 to 1 moles hydrogen, moles nitrogen is equal to 2.141 moles of hydrogen consumed. So then it's just a matter of 19.84 moles H2 minus 2.141 moles consumed. That'll tell you how much is left over. 996.71. So you round that out to your sig figs, you get 17.70 moles of hydrogen left over. Of course, I asked for grams, but I'm running out of room, so it's going to be 35-ish grams. So I don't feel like doing the conversion right there. For those of you who are very concerned that everything be right, it's 35.68. So that is, I should say, a limiting reagent problem. Let's go ahead and make up a problem. So let's go with A plus B2 plus C goes to form AB2 plus BC2. Okay. So now it's balanced. We need to know, well, I can't give you grams, so I'm just going to give you moles directly. If you had 3.0 moles, so 3, 4.0 moles, and 5.0 moles, which one is present in excess, which one is the limiting reagent? So once again, we go ahead and we divide by the stoichiometric coefficients. Okay, so this is going to be divide by 1, divide by 2, divide by 4. When you do that, you get 3.0, 2.0, 1.25. So the smallest number is still the limiting reagent. These two are both present in excess. So just wanted to go ahead and throw that out there. It's possible, but really unlikely, especially if you're just making up a problem off the top of your head. It's possible to have two things share the status of limiting reagent. You know, just if they both happen to have the exact right amount. More likely, you'll have one thing as the limiting reagent and multiple things as the excess reagents. You'll notice that they're in excess in different amounts. This one will have 1.75 left over. This one here will have 1.50 left over. No, technically that's not right. Those aren't stick figs, so there should be 1.8 and 1.5. Okay. So they're not in excess to the same degree, but that doesn't really matter. And let's see, as for how much you'll make 1.25 moles of AB2. You can check my math on this one. And 2.5 moles, 1.3 moles of AB2 and 2.5 moles of BC2. That's what I really wanted to throw out there. Now let's go ahead and talk about percent yield. Percent yield is, well, it's just that the world isn't perfect. The world is a complicated place. Screws fall out all the time, that sort of thing. It's not necessarily the case that a reaction will produce as much as it could. There's little inefficiencies. Let's go here to C3H8 plus 5O2 makes 3CO2 plus 4H2O. This is a nice example. Combustion is rarely a perfect process, just because there's so much going on. This is actually a very, very complicated reaction. It takes place in multiple steps. I don't know exactly what they are, but I know they exist. Because the odds of, 6 molecules running into each other all at the same time is vanishingly small. So instead, you'll have, the propane reacting with one molecule of oxygen, then it'll react with another, then another, then another, and so on. So there's lots of possibility of getting side reactions. Okay, and incomplete reactions. Just because, the propane or the oxygen will react with something else, or, one of the intermediate products, something that you produce along the way, like a C2H4 or whatever, those just won't find another oxygen, things like that. In automobiles, these side products and incomplete reaction products, those were what were responsible for smog. And it was the introduction of the catalytic converter that got rid of smog. So, yay for catalytic converters. So what will happen is that we'll just sort of bundle all of that together and talk about the percent yield as how much you can typically expect to get out of any given reaction. So what you have is the actual yield and the theoretical yield times 100% equals percent yield. So what you actually get divided by what you expected to get if in a perfect world is your percent yield. So let's go ahead and stick with the propane reaction. If you threw in 10 grams of propane, if you combusted 10 grams, what is the percent yield if you produce 5 grams of carbon dioxide? So percent yield equals question mark. Okay, so if you actually produce 5 grams, that means that this is the actual yield. So we need to find the theoretical yield. What mass of carbon dioxide should you have gotten? Okay, so all roads lead to moles. Let's convert to moles. Oops, not times, but divided by 44.09 grams per mole gives us 0.2268 moles of propane, C3H8. Okay, now we have to convert that to CO2. So 3 moles of CO2 per 1 mole of propane gives us 0.6804 moles of CO2. But I gave it to you in grams, so you have your choice. You can convert this to grams of CO2, or you can convert this up here to moles of CO2. Doesn't really matter. You'll get the same thing either way. So let's go ahead and convert this to moles. The molar mass of carbon dioxide, by crazy random happenstance, is 44.01 grams per mole. And that's going to get us a theoretical yield of 29.95 grams of CO2. Okay, so this up here up top, this is our actual yield, so this right here is our theoretical yield. You can already see our percent yield is going to be ridiculously small, far smaller than you would actually expect to get for this, but what that means is that actual over theoretical is 5 grams over 29.95 grams times, 100% gives us 16.7%. Now, when it comes to reactions, what sort of percent yields can you expect? That varies. Okay. Some reactions are incredibly inefficient. Making a particularly difficult organic compound might be 2%. Something that has been perfected by chemical engineers for an industrial process might be something like 99%. You never know. They can vary wildly. Biological reactions tend to be very, very highly efficient just because, they've had billions of years to get really good at it. Okay, so let's look at a different problem. So let's go back to our ammonia problem. N2 plus 3H2 yields 2NH3. Let's pretend that this has a percent yield of 85%. With, let's go ahead and turn around backwards. Okay, if you need to make 20 grams of ammonia, how much nitrogen are you going to need? This one might look kind of challenging, but it's not. This right here is our actual yield. The 20 grams is what we want to get out. So that means that in order to find out how much nitrogen, we're going to need to get the theoretical yield. So we have actual over theoretical times 100 equals 85%. So our theoretical yield is just T is equal to A times 100 over 85, or 23.53 grams of ammonia. Okay, so that's the theoretical yield. The actual yield is 20 grams. The theoretical yield would be 23.53. In other words, this is what we have to shoot for. Aim for the stars, or aim for the moon, so you can land among the stars, right? Whatever that quote is. Okay, so the theoretical yield is 23.53, and that's what we use to calculate how much nitrogen we're going to need. Okay, first we convert to moles, so divided by 17.03 grams per mole is 1.382 moles of ammonia. Again, this is still our theoretical amount of ammonia we'd need. Stoichiometry, where we're going to, goes on top. And that gives us 0.6908 moles of nitrogen. And of course, we multiply by the molar mass. Just because, I'm a stickler for making you guys practice that crap over and over again. Means that in order to produce 20 grams of nitrogen, we need 19.36, grams of ammonia. We need 19.36 grams of nitrogen. So even if I turn this around backwards and give you something that looks confusing, it's not. You just need to determine, is this the actual yield or the theoretical yield? Did he give us the percent yield, or did he give us some amount of product? And if I really wanted to, I could give you 5 grams of A, 5 grams of B, and 5 grams of product, and ask you what's the percent yield. In other words, combining a limiting reagent problem with a percent yield problem wouldn't be too hard. It would just be a little bit of work. In any event, that's it for this lecture. That's it for Chapter 4. I'll see you next time for Chapter 5.